Hello, and welcome to the Academy of Useless Ideas. Today we are refreshing our memory on the concept of convergence in sequences. Sequences are like those handy tools you use to approximate elements of a metric space. But how can we tell if a sequence, let's call it xn, is a winner or a loser? Well, we are looking for a point, which we'll call x star, such that every time we throw an open ball around it, there is a natural number capital N that ensures every xn beyond that point is contained within that ball. Think of it like a concert venue where no matter how small we make it, there are always infinitely many people inside. However, not every sequence is a winner. That's why we are on this convergence mission today, to figure out what makes some sequence converge and others not so much. Have you ever noticed how limits are like jealous party hosts? They don't want to share the spotlight with anyone else. So, if there's more than one candidate for a limit of a sequence, it just can't converge. Take the sequence -1 to the power of n, for example. It's like there are two potential parties in town, so the sequence can't make up its mind on where to go. To help us understand the situation better, let's relax the definition of convergence a bit. Instead of requiring that every except for finitely many elements on the sequence lie inside the open ball, we'll only require that finitely many elements lie in the ball. Now that we know that some sequence may have multiple candidates to a limit, we can introduce the concept of subsequential convergence. A sequence xn subsequentially converges if there exists a point x sharp such that for every ball around x sharp and for every capital N, we can find a little n larger or equal to capital N such that xn belongs to that ball. In other words, the sequence gets infinitely close to x sharp, even if only a subset of it does. We call any x sharp that satisfies this condition a subsequential limit of xn. Unlike limits, subsequential limits are not jealous. It is like letting each element of the sequence decide which concert they want to go to. The concept of subsequential limits naturally leads to the notion of subsequence. A subsequence is a new sequence created by selecting only some elements of the original sequence. It's like choosing which people to invite to each party. If x sharp is a subsequential limit, we can construct a subsequence converging to x sharp by choosing one element in the original sequence for each ball of radius 1 over n. In fact, we can construct a subsequence converging to each one of the subsequential limits, but we'll get to that in a moment. Before we dive into the formal proof, let's refine our understanding of what a subsequence is. It's like making a playlist of your favorite songs from a larger library. To create a subsequence, we need a function that helps us pick the elements of the original sequence. We call this function sigma, and it maps natural numbers to natural numbers. But we can't just pick any function. We need one that is strictly increasing. That way we know that we are always selecting elements that appear later in the sequence. Think of it as building a VIP guests list for a party, but only adding people who are more important than the ones already on the list. Now, since a sequence is just a function from the naturals to some space, we can use sigma to create a new sequence, which is our subsequence. We pick elements from the original sequence by using the values in sigma as indices. That's why we write the subsequence as x sub n sub k, where k is the independent variable and nk is the strictly increasing sequence of natural numbers that we used to pick the elements. It's like creating a guest list for a party. We only pick the guests that are going to the same party, in this case, the ones that converge to the same limit. Now that we have our definitions in place, we can prove the obvious fact that x sharp being a subsequential limit of xn is equivalent to the existence of a subsequence xnk that converges to x sharp. To see why, let's assume that x sharp is a subsequential limit and pick n0 equal to 0. Assuming that nk has been chosen, we can pick nk plus 1 larger than nk, such that xnk plus 1 belongs to the ball of radius 1 over k around x sharp. The existence of n sub k plus 1 follows from the fact that every ball contains infinitely many elements of the sequence xn. For the other direction, assume that the subsequence x sub n sub k converges to n sharp. This means that for every ball around x sharp, all but finitely many elements of x sub n sub k lie inside the ball. But that also means that there are infinitely many elements of x sub n lying in the ball. We can prove that if a sequence converges, its limit is a subsequential limit and it is the only one. This is because if there were two different subsequential limits, then you could find a pair of open balls separating them, and such that infinitely many elements would lie inside each one of those balls. But then none of those points could be the limit because the limit only leaves infinitely many elements outside any such ball. However, the converse is not true. That is, the set of subsequential limits could have only one element, and yet the sequence might not converge. Can you think of an example in which that happens?